Welcome to the 25th class meeting of the Introduction to DSP. As usual, homework will be assigned, and there will be more and more MATLAB homeworks, so be prepared. For the voluntary project, please let me know your topic for the project. It must be approved by me, otherwise I will not accept your project report. We are currently studying chapter 9, and I hope we can finish this chapter today. And I have found that the so far uploaded PDFs does not have any file for chapter 10, so I've just uploaded it to the course webpage, so please download it. The review is very simple. Last time we studied the decimation in time FFT algorithm, and we've learned a lot actually. So the most important two keywords were what? The symmetry and the periodicity of W sub n raised to the power of nk. Here, e to the negative j 2 pi divided by n is defined as the W sub n, which is used in the n-point DFT. And by exploiting the properties of this constant, you can say that this function of n and k, we could divide the n-point DFT into two n over 2 point DFTs, and we repeat that procedure again and again, and eventually we have big O of n complex multiplications and additions per each stage, and we had log 2 base n, which is in our case of n equals 2 to the nu, was the value nu. So we have eventually had n log n computational complexity. Got it? So that was the idea. In order to do that, we introduced a lot of tricks, and one of the trick was related to so-called butterfly computation. And if you don't remember that, let me show you the figure that corresponds to that idea. So this is the so-called butterfly computation idea. So the m-1 stage to m stage, here we have two constant multiplications, but by using this property, we could reduce it to one complex multiplication. And this is called butterfly computation to reduce the number of complex multiplications. So we could basically had the idea of reducing the complexity from big O of n squared to big O of n log n to build the decimation in time FFT algorithm. And it could be directly applied to decimation in frequency FFT algorithm. So I briefly talked how to do that. And today we are going to see some complexity comparison when n is not necessarily the power of 2. And also, we will see section 9.6, which is very closely related to the FFT algorithm. But the importance of this algorithm, chirp transformation algorithm or chirp Z transform, increases, especially in digital communications, where we consider so-called high mobility, which means high Doppler shift, Doppler frequency shift environment, where we need to estimate not only the delay and complex gain of each multipass in digital communications, but also we need to know the velocity of or speed or equivalently Doppler Doppler frequency shift amount of each pass to correctly estimate the channel and also compensate for the effect of that nonlinear frequency shift. And also in so-called integrated communication and sensing, or sensing and communications, ISAC, where we want to combine digital communication and radar, especially for this sensing means usually radar. We not only need to find the presence of some target, but also want to know the amount of mobility which relates to the velocity or speed of each object. In that case, estimating the amount of Doppler frequency shift is very, very important. And your use of chirp Z transform or chirp transform algorithm related or based some algorithms plays an important role. So today we are going to see this. And if time allows, then we are going to move to chapter 10, where the title itself is about the kind of application of DFT, basically FFT algorithm for various variety of Fourier analysis. Got it? So this is the big picture of what we are going to see from today and this week. Let's see. Where are we? Yeah. So the section 9.4 is entitled as the practical considerations. And as I told you, this book was initially written around the early 90s or late 80s. So it's almost around, how to say that, a quarter century ago. So, so far, the technology to build digital signal processors has evolved a lot. So at that time, the DSP chip has very small size of memory. As you remember, even the Bill Gates, when he initially developed the MS disk operating system, 640 kilobytes he believed was enough for personal use. And probably you may say that what 640 megabytes is not enough, you may say that, right? Or, 640 gigabytes or terabytes of memory I want. So you must understand, even though our textbook says something, that may not be true any longer, or that may be, how to say that, highly mispredicted the future. Right? Anyway, so this section talks about data storage and why that happens. Because in order to compute the FFT, anyway, you need to form a vector. If you directly apply, for example, decimation in time or decimation in frequency algorithm, you need to store these samples, especially when the number of points is large. At that time, large means 4096. It was large enough at that time. You have to have around 4K memory cells to store those input vectors alone. And also, in each stage in the FFT algorithm, you have to multiply complex number, which means that you need to store intermediate value. And also, eventually, you have to store the output vector of length n before you dump it over to some other system. So they talk about the importance of the storage or even some design of circuit board to efficiently implement the system. So, and here, the programming and system design means that now you use, for example, Python, and just you download some module that performs FFT. So you don't know how the coder or programmer really implemented the FFT in which way, you don't know. But suppose that you are the person who implemented that initial Python module to do signal processing, including FFT, then probably you would have gone back to the textbook you used in the undergraduate study and follow the procedure to improve the speed of your code, something like that. And also, when they have very small computing power, this managing the storage was very, very important. But as I told you, most of the concerns are now gone due to the thanks to the development of the high-speed, low-cost memory chips and CPUs and other computing processing units. Anyway, so let me just tell you about the complexity only. So as you've seen, when the number of points n is a composite number, which means that a product of some numbers, 2 numbers or 3 numbers, and especially when n is the product of prime numbers or n is itself a prime number, then it's not a, if n is just a prime number, that is the worst case. So here, this is the so-called flops, number of flops. And by the way, this metric, flops, is not much used compared to this time of when the textbook is written. But when I was an undergraduate student and even graduate student, research papers showed flops, number of flops, and some parameter. In this case, the number of points in FFT. And I don't know exactly why they almost abandoned this metric. But anyway, let's see. So here goes the curve that is quadratic in n squared. And they say that this point lying on this line is the cases where the number of points is a prime number. By the way, I still remember the shock when I had when I took the GRE, the graduate record exam, to prepare for my studying abroad. So, for example, if you want to have a graduate study in the United States universities, you not only need TOEFL, test of English as a foreign language, they usually ask you to provide a GRE score. GRE is a kind of some largely exaggerated version of TOEFL for graduate students. So it not only has reading comprehension. It has some math part, but this math is very, very simple. And the level is around the middle school math. And at my time, there was so-called analytics. And this was more like an IQ test. And it's like there are 5 students named A, B, C, D, E, and when A saw the B, he or she was on the right side, blah, blah, blah. And then who is the person next to the person C, something like that. Anyway, this math was so easy, so I didn't prepare much for that. But before you take the exam, usually you have simulated test, and I lost one problem, and that was related to so-called a prime number. What is prime? Probably you know some prime rebel, you may say the important something, but I didn't know that this means so-called SOSU, something like 2, 3, 5, 7, something like that. So prime number is SOSU. Anyway, so in that case, we cannot avoid the complexity of big O of n squared. And this is a kind of upper bound, And here goes the lower bound, n log n, big O of n log n, where n is the power of 2. And you see there are many other realizations having the computational complexity between these two curves. And they are composite numbers. N, like for example, n equals 6 has two prime numbers product, and then you have in between these two. Of course, when this n is very small, the difference between these two are not that much, but consider the case where your n is around 250, then probably this is 256, as you know, and I'm not sure that which one is prime number close to 256. But anyway, there is something. 249 is a prime number? No, it's a multiple of 3, then what it is? But anyway, I don't know. So you see that these composite numbers have higher computational complexity of big O of n squared. So what do we do? Sometimes we so-called do the zero padding trick to make the number of points 2 to the 2 raised to the power of something. So we really prefer 1024 point FFT instead of 1000 point DFT. Got it? Even though this is a kind of whole number after so-called round number, I do not exactly know, right? But round number, this is much better. So we pad the zeros to make the number of points power of 2. Anyway, so this figure, given this figure, you need to remember 2 lessons. One is that sometimes once very popular performance metric is totally obsolete and almost no one seriously uses this one. Of course, it's very useful because still the MATLAB has a function to show number of flops, even though they say that this function is going to be taken off. Got it? And second one is that whenever you show the performance metric, it's better to have lower bound and upper bound. And that gives you a better edge in the review process. Anyway, by the way, there were some typos, n squares and n squares. Anyway, depending on the machine architecture, you can optimize the FFT algorithms. But these days, as I told you, there are many even AI-based layout design programs and other systems that has a lot of computing power. Sometimes we just use general purpose machines so that we just compute almost everything using software, not hardwired circuits. And also those general purpose machines is going to be reused for other purpose. So it has kind of excessive computing power than is required. Once I told you, I was shocked to find that the so-called the 선거관리위원회 has the sorting machine, and since there were some people doubt about the integrity of the machine, so the 선거관리위원회 showed what is inside the machine, and amazingly, the brain of the sorting machine was LG Gram notebook. There were no other electronic device except some controllers for the motors that controls the spindles. So it was amazing. And also, after the election is done, I've seen some news saying that the Korean NEC, the 선거관리위원회, sells computers they used for specific elections after wiping out all the records in the machine. Anyway, usually the important elections occurs once per 2 years, and after 2 years, the machines will be kind of outdated, and also a lot of people has doubts on the old machines having some malwares. So it seems that they sell the machines in a very low price. Anyway, okay, here goes the next section entitled Implementation of the DFT using Convolution. And I read this one before coming to the class meeting, and even though the authors say that there are some cases where we need to use convolution to implement DFT, they claim. So it's kind of opposite, right? So we want to use DFT, actually FFT, to reduce the complexity in convolution, but this section entitled exact opposite. However, I'm not sure whether there are some serious people who really want to exactly follow this title. As I told you, the trend is more and more implementation of something using FFT or DFT, because FFT is so powerful now. So I will explain this section more the reverse way, even though the title says implementation of DFT using convolution. So what kind of application we are thinking about? So this figure is the key, and you need to remember. I was first exposed this chirp transform algorithm when I was at your age. So in my last undergraduate semester, I took the introductory DSP course, and almost at the end of the semester, the professor talked about this one, just showing us the figure and talks about what's going on. And that was all. And since I was in the communication area, there were some cases people talk about chirp transform and chirp signal, something like that. So this figure was not completely forgotten from memory cell. And amazingly, around after 30 years later, when I was doing some project, I remembered this figure. Hey, I remember I've seen chirp transform from the DSP textbook. And of course, I'm a professor. I asked one of my graduate students to look up that one from the textbook. And he studied this one and exactly followed and kind of combined this use of FFT to significantly reduce the complexity in computing some estimate in our channel estimate. So let's see. But the trouble is that our textbook shows chirp transform algorithm, not the chirp Z transform. So I've attached the Wikipedia page here. So let's take a look at this. I didn't add this in our PDF file, so you need to visit the Wikipedia and find this page. So first, we want to define so-called the chirp Z transform of what? Of a discrete time signal X. Here, our Wikipedia use parentheses instead of square bracket to enclose the time index n, but you know what it means. And also, I have found that I really wanted to revive my Wikipedia account to modify this page, because in one side, our textbook is more general in the sense that when they introduce the chirp transform algorithm, they want to evaluate the chirp Z transform in capital M different frequencies for length n vector. the trouble of this Wikipedia page is that they set n equals m and explains the material. So I really want to revive this my Wikipedia account to modify this page, but I'm not sure. Probably in 1998 or something, when Wikipedia first came, I opened my account, and I don't know what was the email account linked to that account. So yeah. Anyway, so when you yourself study this page with the textbook, please be careful that our textbook assumes the signal is of finite duration, n, okay, this is duration, and our authors of the textbook wants to sample at m different radiant frequencies. So this is more general setting, but the page has n equals m. Anyway, so here, this looks more like Z transform, but here, G sub k is actually A times W raised to the power of k. And be careful, here, A is a general, non-zero, complex starting point, which means that is not necessarily 1, not necessary. So our textbook had the unit circle, and let me show you again. Yeah. The points on the unit circle, but this chirp Z transform has more general setting. So maybe you have something like this. So even though your angles are the same as delta sub, I remember omega's delta sub omega, following our textbook, but the magnitude may be different, like a square, a cubed. Yeah, something like this. So this is more general than what is shown in our textbook. But anyway, so it's more like general Z transform of our discrete time signal, where Z equals, as it shows, A omega, sorry, AW minus K. Got it? And this is renamed as Z sub K. And here, okay, just a second, let me see. Just a second. Yeah, so far it has M. Why just a second, some things. Yeah. Okay, got it. So far, let me retract my claim. So here, so far, it is not, they are not yet equal, not yet. So N is duration, M means different radiant frequencies. But here they explain in the next section of Bluestein's algorithm, they said N and M the same. Okay. Anyway, so here we have general Z transform of a discrete time signal, which involves countably infinite terms. But suppose we are handling a finite duration signal, in that case, we may properly shift the initial time index and the final time index. So we may have lower limit 0 and upper limit capital N minus 1 after proper shifting or delaying or advancing. And we want to evaluate this capital X of Z on some complex number. Got it? So, by the way, why we have this special point? We got just the same, we may say that G sub K and G sub K's are some points on the Z plane. Because in this chirp transform algorithm and in the chirp Z transform, the phase angles are equally spaced. We assume that. So let's think about A as a real number, real positive, and W as some complex number. Then W has what? Magnitude and phase angle. So G sub K is basically A times R raised to the power of K and e to the negative J theta K. Got it? So these GKs are what? Has the uniform spacing. By the way, A may have extra phase if we assume that this has A e to the J theta 0. Okay. This is more general. So as I've shown here, this Z sub 1, Z sub 2, Z sub 3, Z sub 4, Z sub 5 may have exponentially increasing magnitude, but has uniformly equally spaced phase differences. And of course, the special case where the magnitude of number A is 1, then it reduces to our case shown in the textbook. Got it? Sometimes you need this one, or sometimes you may need a more general version. So please remember, it may save one of your projects within 30 years. So you are around the 25, right? So less than 25. So I hope your engineer's life continues up until 60s. Anyway, so this is the idea. And what is the trick? The trick is exactly actually Gottzel's algorithm. So the G transform or chirp G transform output is regarded as the LTI system's output. So what they do is that they compare this summation with some convolution of two signals. And they want to find proper Z and H. And of course, they want to modify this upper and lower bounds of the lower limits of the summation to finite numbers whose magnitude is as small as possible. Got it? And they want to say that this is somehow related to x of n. The problem is that usually they use index k, especially in this case, need to modify all the indices like this. It's very confusing. And interestingly, I'm not sure why, but our textbook, even they explain almost the same thing, they start with index k and eventually modify the index to n. So it's very, very confusing. So be careful. Now let's see our handout. Here, as you see that the x of n is finite duration discrete time signal, or it may be from the beginning was a finite length vector. And we converted it to a discrete time signal by padding countably infinite number of zeros. Anyway, by doing that, we can connect the DFT of the vector with the DTFT of that discrete time signal. I've repeatedly told you. And here, unlike the Wikipedia, where they introduced the chirp Z transform, the textbook has what? Chirp transform, which has what? The complex number Z sub k has unit magnitude. That's why there is no exponentially increasing or decreasing magnitude. But anyway, they wanted to choose capital M different frequencies with frequency index k. This is kind of x of k in the Wikipedia page. Got it? So don't be confused by the indices. Anyway, very similar to the Wikipedia page. This complex number has what? If it is plugged in here, it has linearly increasing phase, which means that the complex points, we want to evaluate the Z transform of the discrete time signal lies on the unit circle with equal spacing. Okay? So by defining W as e to the negative j times some delta omega, we may rewrite this line as this one. Now they compare these two. As I told you, usually we love n like this, right? So this is the convolution of G and H discrete time signals. But they start from K, so let's consider this one. And what you want to do is that somehow from here, in this summand, we factor properly these things, and we define G and H. And what we are going to do is that here goes xn sequence signal, and here is some discrete time, probably LTI system, and whose output sometimes sampled. That's what we've seen in Gottzel's algorithm. Or amazingly, in this case, we just need single LTI system with two modulators. In that case, we just need to observe the outputs of this combined LTI system m times, because we want to have m different frequencies. But anyway, so let me highlight, this index k, otherwise it's very confusing. You remember in the Gottzel's algorithm, we have a bank of LTI systems sampled at the same time instant to generate the DFT output. This has slight difference because of this property where we consider something like this. So let me repeat. This is Z sub 0. This is Z sub 1 to up to Z sub m minus 1. So we want to obtain capital M Z transforms. Got it? And the starting point is this one. So we initially have the gradient angle, omega sub 0. This is omega sub 0. And from that, we have uniform delta omega spacing. Got it? And you may wonder, hey, what's the difference? This looks more general than the Gottzel's algorithm where they wanted to compute the DFT, right? Because if we may set m equals m and delta omega as 2 pi over n, then what's the difference? So this somehow shows how to modify Gottzel's algorithm to use FFT. But actually, Gottzel's algorithm was to reduce the complexity of DFT. So it's like which one is first, egg or hen, something like that. Anyway, so here goes the trick. And this trick not only appears in our textbook, but also appears in the Wikipedia page. So basically, this Wikipedia page is a kind of generalization of what is shown in our textbook. So whenever you have two variables multiplied, then you may rewrite this as the second order terms like this. And you know how does it work, right? Because this is the well-known k square minus 2kn plus n squared. So if you add this and divide by negative 2, then you have nk. And you may say that, so? And here goes something interesting. So we plug this product, now rewritten in this form, where here. Got it? And if we rewrite the summand of the summation, we have x of n, as you've seen here. Now you have e to the negative j omega 0 n, right? So this is just the rewriting of the last factor in the summand. And they propose to group the first three terms and the last one and take this out from the summation. Why? Because see that the summation is over the variable n. So this one is just related to this index k, so can be taken out of the summation. That's why you have this one, when still you have the index k. Got it? And now, since it has n square, the original algorithm, probably Bluestein's algorithm, original algorithm was to compute the chirp, not the chirp transform, but just the chirp transform. The three factors is grouped. The three factors are grouped to signal g of n. And this one naturally has k minus n in the exponent. And you see that when the index is k, we want to find k minus n. And here is k minus n. Got it? So this signal can be viewed as h of k minus n appearing here. Got it? So Since we have defined this as G, factoring this out, and this as h sub k minus n, eventually we have what? We have here this one, which is the convolution of G and H. Be careful, still our time index is K. So up to this point, we focus on omega sub K, and K runs from 0 to n minus 1. But when they show the block diagram, they go back to n, much to our confusion. So here goes x of n. And now let's see. What is this one? This one is here. The difference is that since we have changed the index to n, right? This w n squared divided by 2 appears here. Now, what is g? G is x times this signal. So here we have this one multiplied to x to become g. And now g and the LTI system with impulse response w sub, this is not good. Okay, let me use this one. W sub w raised to the power of negative n squared divided by 2 is convolved. So we have eventually x evaluated at e to the j omega sub n. Got it? I haven't yet determined whether this is correct or not, but it seems this is correct after we properly scale. And interesting thing is that we just need to evaluate n for capital M values. And you may say that, wait a minute, in Gottzel's algorithm, we had a bank of LTI filters. Now, in this special case, we have what? A single LTI system, linear time invariant system, but these multipliers with time varying signals are linear but not time invariant. Ready? So be careful. In chirp transform algorithm, or similarly in the chirp Z transform, what we do is that we convert the transform to what? A linear time varying system that consisting of what? Time varying signal multipliers and an LTI system. Got it? And here diverges our textbook and the Wikipedia page. The authors say that, hey, we have successfully transformed our chirp transform to a linear system. So sometimes we can implement like this. If our frequencies are not 2 pi divided by n and are subset of, for example, some of these 2 pi over n sequences, something like that. However, as I told you, and also as our Wikipedia page says that, now this is not the story. By the way, our textbook says that the more general form of chirp transform algorithm is called the chirp Z transform. And as I told you, the Wikipedia page is about chirp Z transform. And now, since you've seen our textbook, let's see and find the difference. As I told you, Z sub k, the different points on the Z plane on which the Z transform is evaluated is not necessarily on the unit circle. The commonality is that they are uniformly equally spaced, but the magnitude may be exponentially increasing or decreasing. Got it? So in this case, in this sense, this chirp transform is a more general version of the chirp transform algorithm. But the idea is the same. This is the idea of blue stain. So the key is replacing this product in the exponent, the nk, as what? As in this form. And you somehow factor some part out of the summation and define the summation as a convolution. Then what do you have? You have input modulated somehow, convolved, and modulated again. Got it? That is the idea. So as you see that the convolution and some multiplication, very, very similar to, where it is, to our case. Got it? Not much difference. Now, you may still have why these two algorithms almost the same, except the magnitude. Why they are called chirp transform. And the reason is because of this signal, or you may say that signal. And probably you know this verb chirp. Chirp in Korean as a verb, 동사로서, so-called 세가지적이다, 짹짹거리다. And why this is called chirp? Because suppose you consider something like this. And you may say that, hey, professor, you have a type of, actually it is not. This is plus. And I'm not sure, just a second. Is it delta? Oh, okay. Some constant, alpha. Okay. So it's actually cosine, right? 2 pi f0 plus alpha t times t. And you may view this one as so-called instantaneous frequency. So your instantaneous frequency increases linear. And people have found that such a signal, especially if it repeats, it sounds like jack, chop, chop. That's why the signal is called chirp signal. So this is a chirp signal. And now let's combine these two factors. Then what is the key? This F0 t gives us kind of reference frequency, but the key is what? Some constant times t squared. Got it? So whenever you have e to the j times some constant times time index squared, then you may name the signal as a chirp signal. Now, let's take a look at here. As k as the time index, this is what? This is a chirp signal. What is this one? This is a chirp signal. Got it? So this is called the chirp transform. Let me repeat. Here, with some special limitation on g sub k, after handling, you may write in this form where you have a chirp signal and a chirp signal. Got it? Of course, this is the key. The impulse response is also a chirp signal. Got it? So you have three chirp signals involved in this chirp G transform. Got it? Anyway, I'm not going to give you a specific example where you may find the application of the chirp G transform or chirp transform algorithm to estimate the Doppler frequency shift. You probably, if you continue your career as a communications engineer with this era of high mobility, fast, high-speed train or high-speed drones, high-speed satellite, probably you will confront this chirp transform or something related again in your near future. Got it? Anyway, so this is the main idea. By the way, here goes some details. So we've seen that the such a system with impulse response, this one works, but you may say that, is this impulse response of infinite duration? Then what does that mean? So actually, since you need the output only for finite samples, actually you can discard countably infinite terms from this infinite signal. And from the fact that you have only capital N of X non-negative, possibly non-zero, and you evaluate for capital M positions, here goes the idea. And you yourself find it, okay? H of N may be assumed to be of finite duration. And what was N? Length of X. What was M? Number of different radiant frequencies, right? And of course, the authors kindly says that, hey, if you really want to implement this using a delay component and memory, like you implement the system using linear constant coefficient difference equation immediately, then you need a causal system. So why don't you delay the impulse response so that you have a causal system, something like that. So they also talk about this causal implementation method. But as I told you, probably no one in this time will implement DFT or chirp transform using this linear constant coefficient difference equation, of course, combined with two modulators. Rather, they want to evaluate the chirp Z transform using FFT. So let's see how we do this. The idea is very simple. As you've seen, we have finite duration signal, X. So let's say X as length N. And we want to evaluate for capital M-1 positions. Then what do we do? As you've seen that the H has length M plus N minus 2, if I remember correctly. So in order to convolve with H with G after you multiply some sequence to make X2 convert to G, right? Still, this signal G is of length N. So you have some G that ranges from 0 to N minus 1. And you have H of N that starts from, am I correct? M minus 1 to N minus 1. So you need to cut this signal G from some 0 to L. And you need to cut this H again from 0 to L, right? And you know that the convolution of this signal with that signal may have length, this plus that minus 1. So you need to choose L greater than or equal to that length. Of course, by using the fact that you only need m minus 1, you may reduce the length, but the simplest approach, because we have enough computing power, is that the L is chosen as the summation of these two lengths. Then it's usually enough. So you pad a lot of zeros, and what do? Instead of computing the chirp Z transform directly, you perform FFT on this vector, FFT on that vector, and you multiply, and then you perform IFFT, and don't forget, you multiply this chirp signal, uniform chirp, okay, to have the desired signal, and then you discard a lot of terms. Got it? So this is the case where you have enough computing power with enough memory. That is the case now. Got it? So that's why we are not following our textbook to simplify our implementation, because now we have enough memory. We can use very large size FFT. So almost everything is now converted to be used by the FFT algorithms. Got it? Anyway, it's like, how do you say that? In Eastern Asian, how to say that? Forward phrase says that, or something like, 백문이 불여일견, something like that. 백문 불여일견, 6 word, 6 character. But anyway, you will find it, how to use it when you do your MATLAB homework. Got it? Okay, I'm almost finished. So they also talk about the effect of finite register ranks, blah, 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 but let me omit. But just remember that, okay, our textbook was very carefully written to reflect all the important facts to be considered at that age of the book being written. Got it? Okay, I believe I've done, yeah, chapter 9. So we have around 10 more minutes. So let's move to very quickly to chapter 10. Chapter 10 is again about the application of DFT for various signal processing. And you may interpret the title as what? Application of FFT. Because anyway, we really love the number of points, the power of 2. So this is the kind of big picture. And here we've covered chapters 8 and 9. Now we see more about the application of FFT. So the title of first section is Fourier analysis of signals using the DFT. And you may say that, hey, we've already done this. You are half correct. So let's see this block diagram. Suppose you have a continuous time signal. And now you want to do Fourier analysis on this continuous time signal. Got it? So what do you want to do? You want to, sorry about that. You want to compute the CTFT of the signal, not the DTFT of some discrete time signal. But we assume that we have what? Sampling. We sample and then use DFT to estimate the CTFT of the signal. Of course, we assume that this anti-aliasing low-pass filter, we hope, does not cut out some information here. Even if it does, we may be interested in the frequency contents within the passband of this anti-aliasing filter. And here you have continuous time signal. So you may say that we are interested more on this one, but it's almost the same. Here goes the uniform sample actually. So sampling period or sampling rate is involved in this conversion. And here goes something strange, but actually this is called a window function, which is usually time limited. And for simplicity, we assume that this has length, duration, n. For example, if this is a rectangular window of duration n, then you have all ones and all zeros before and after this period. Got it? By the way, this is, of course, the rectangular window. And you will see some troubles related to this one in other sections. So people have found the rectangular window, even though very simple, sometimes introduces so-called artifacts. In Korean, how to say that? Yeah, I don't know the exact Korean word, but it's similar to hallucination in AI. Okay, so there was no such a frequency component originally, but using the rectangular window, we have some sudden high frequency term, something like that. So there are other window functions. Some important windows are Hamming windows, Hanning windows, Kaiser, Blackman, and some others. There are many windows. And you now know why there could be some many windows, because these windows are not all perfect. They have their suitable applications. So anyway, now we have windowed signal, and let's assume this is time limited. So even though these are all arrows, you know that this arrow means continuous time signal. This arrow also means continuous time signals flow, discrete time, and actually this is, even though discrete time, actually this is discrete, means vector. Got it? So actually vector goes into the DFT block, and you have vector comes out from this block. And the question is, by using this one, estimate the CTFT. Got it? And of course, this one may be visualized using STEM, for example, real part of B, imaginary part of B. But what was our objective? We wanted to, for example, visualize the CTFT of X of C or S of C. So our textbook naturally says that, okay, let's illustrate this one and also linearly interpolated version of the vector. and you will see something like this. So it's like in MATLAB, you use stem function and just the plot function here. And how many samples do you have here? The number of samples is related to the window length or point of DFT. So if you have larger and larger n, then you have larger and larger output and larger points to be linearly interpolated. Is that good or not? It depends. But suppose you have fixed sampling period or sampling frequency, then large size DFT gives you a lot of benefit. That is the key actually, because the radiant frequency of this discrete time signal is translated to the continuous time signal via the sampling frequency. As you know that this discrete time signal is periodic. If you use radiant frequency, it is periodic with period 2 pi, right? So x of n has DTFT like this. Now, what is the relation between the CTFT of this one and DTFT of that one? As you remember from the sampling theorem, this is actually half the sampling rate in the continuous frequency. So this is discrete time, the DT radian frequency, and this is CT radian frequency. So they are equivalent in that way. So as far as you fix this sampling rate, but if you increase the window size so that you have more and more points to be discrete Fourier transformed, you have more and more points evaluated in the DTFT, which means DFT. So your linearly interpolated curve will more well reflect the CTFT. So this is what you need to remember. Sometimes your problem would be, given this signal, design the anti-aliasing filter so that no information is lost. Design or select this sampling rate, select the window length to estimate the CTFT from DFT. In that case, there are too many parameters, right? But the key is, and what you need to remember is that this sampling frequency corresponds to pi, and negative sampling frequency corresponds to negative sampling frequency by 2 corresponds to negative pi. And number of points evaluated is related to n. As the name says, n-point DFT. You have n-point resolution. Got it? So if you want to have more higher and higher resolution, you need to, of course, you can obtain that at the cost of high computational complexity in your DFT operation. And it makes sense, right? Anyway, so time's almost up. So there are too many things to talk briefly, like effect of windowing. Let me stop here and continue on Thursday. Okay, that's all for today.